So we are very pleased to have this next session, which will be again about climate change. I actually also on biodiversity a lot. So it's a good combination of the two themes of this workshop today. So I'm very pleased to introduce Frances Moore, who will be giving the first talk of this session today.
Great, thanks so much for having me here today. And I'm sorry I can't be there in person. It looked like a really fascinating conference, and I'm just sad it was like mostly in the middle of the night where I am here in California. So today I'm going to present some work that I did with my PhD student here at Davis, Bernie Bastian Olvera. And what we're thinking about here is these measures of kind of aggregate climate change costs. How do we begin to seriously incorporate and try to incorporate some of the values, some of the ecological impacts and the damages from climate change to the values that we get from natural systems? So the motivation here is that, the disruption of ecosystems by climate change will direct, long-lasting and widespread, and to a kind of at least first approximation irreversible. So for example, at 3 degrees of warming, between 10 and 40% of terrestrial vegetation will be severely disrupted, and 8% of species will be at risk of extinction. But I think it's fair to say that the implications of these changes for human welfare are still poorly constrained, and that they are not well represented in our current estimates of climate change costs. If we think about what these welfare benefits are, I'm going to broadly divide them into two categories. So use values, where we're thinking of kind of recreation, aesthetic enjoyment, kind of pollination, these kind of what's generally called in the US ecosystem services. And what climate change will do here is going to move, degrade, disrupt kind of natural systems and then the ecosystem services that they provide. And as an example here is the kind of widespread tree mortality events that have been linked to, many of these have been linked to climate change, either by drought or kind of expanded pest ranges. Then we're also thinking about non-use value. And so here we're getting into things like the existence and bequest values of species or of particular ecosystems. And so under climate change, a large fraction of species is going to be committed to extinction. And this is already happening. So there's one species level extinction that's being although it's debated, it's being linked to climate change. And species have been entering onto, in the US, the endangered species list due to climate change threats. So the question we're asking here is, how does accounting for this imperfectly substitutable nature of ecosystem benefits affect the social cost of carbon? Where the social cost of carbon here is this measure of the aggregate cost from the marginal ton of greenhouse gas emissions. We're drawing on some prior work, and I'm not going to mention it. This is a shorter talk, so I'm not going to be able to dive into it here, but there's a fairly long literature about, literature going back a long way, but not necessarily super extensive or super well known, about kind of imperfect substitutability of goods. And in general, these authors are thinking about environmental goods in the utility function and how that affects the social cost of carbon. There's also been some previous work on kind of the ecological cost of economic production separate from climate change and how that interacts with climate change effects. And what we're going to do here, we're going to introduce a number of new things into the social cost of carbon estimates. So we'll incorporate the dependence of production on natural capital. We'll introduce a damage function onto natural capital, that natural capital stock. We're going to decompose these use and non-use values. And we'll conduct a comprehensive sensitivity analysis because there's a lot of uncertainty in these parameters. And then finally, we'll explore the role of adaptive investments and savings into the natural capital stock. So here, for those of you kind of less familiar with the kind of workhorse models in the space around calculating the social cost of carbon, I'm just giving a schematic diagram of the DICE model developed by Bill Nordhaus and still in extensive use today to calculate the social cost of carbon. It's a very simple model. There's a kind of two-good production function that produces output. That economic output is split in an endogenous savings decision between investment that goes back to replenish the depreciating capital stock and consumption, where consumption is the only thing that contributes to welfare. then output also results in the climate change externality that produces emissions that contribute to rising global temperatures. And in turn, there's this damage function that economic production. What we do here is we expand this model in several ways. Is there a question, sorry?
No, there isn't, but there is some echo.
Oh, sorry. Okay, sorry. So we split out a natural capital stock, and what I'm going to do, we make several changes, and I'm going to layer these up one by one. And when I present them, I'll present each of those changes so you can see how each of those kind of individually contributes to the results that we're getting. So the first change is that we split out natural capital and we allow it to enter into the production function, changing the production function from a two-good production function that depends on labor and manufactured capital into a three-good production function that now also depends on the stock of natural capital. In addition, we introduce a new damage function here that allows warmer temperatures to affect the stock of natural capital. And so you can already see that what we're going to do is we're going to introduce kind of persistent damages from climate change to the natural capital stock. They're going to have long-lived effects on production. In the second model, called what I'll call the all-use values model, we also introduce a second consumption good, which we're thinking of as kind of non-market ecosystem services, which these also depend on the three factors of production. But what you see is like we switch the gamma 3 and gamma 2 here. So this is indicating that these goods that depend much more heavily on natural capital, since gamma 2 is much larger than gamma 3. And here we kind of allow these goods to be partially substitutable in the utility function. And so this is very similar to the utility function used by some work by Thomas Sterner in previous papers. And then finally, in what the full model, what we're calling green dice, we allow the stock of natural capital to enter directly into the utility function. And so this is representing a set of non-use values that people derive directly from the natural capital stock, independent of any kind of economic production. And so now we have a three-good utility function in which we use a kind of nested CES utility function, where there's a bundle of consumption goods, right? The ecosystem services and the standard consumption goods in a nest, and then those are partially substitutable again with these non-use values that come directly from the stock of natural capital. Okay, so there's a lot going on in this model. I'm going to run through the parameterizations really briefly. The substitutability parameters are partial substitutes based on a meta-analysis by Mark Strupp. We estimate gamma 3 based on natural capital accounting literature. We allow for declining marginal non-use values using a gamma 0.5 gamma 4 coefficient. Our damage functions are based on a kind of meta-analysis of the calibrations from DICE. And what we're trying to do is we're trying to match the DICE calibration point at 2.5 degrees of warming. A stock of natural capital come from World Bank estimates. And then we just have to assume stuff about the utility function because there's no empirical estimates for that. Okay, so let me show you results then. So this is showing you those gradual additions to the standard DICE model that layer in these increasingly layer in these benefits from natural capital and these damages to the natural capital stock. And what you're seeing here is all those kind of additional model runs, and I'm showing you the optimized carbon tax, and then in parentheses I'm showing you also the carbon tax, the optimal carbon tax in 2020. And you can see that, we even just allowing for the stock of natural capital to enter into the production function independent of any use values, you get a big jump already in that 2020 social cost of carbon. In the full model, the social cost of carbon goes up by over 5 times. What that means then is that these kind of much higher carbon costs, the much higher cost of greenhouse gas emissions, result in very different emissions trajectories over time. And so the dotted line here is the standard kind of climate policy ramp emissions trajectory, with emissions peaking around the mid-century, whereas a full green dye specification kind of reaches net zero emissions by 2050. Oh, and I should say the green line is showing you a measure of uncertainty that I'll talk about later on. What that much more rapid emissions reduction does is stabilize temperatures kind of well below 2 degrees, if not below even 1.5 degrees, compared to the optimal DICE emissions trajectory that includes warming of up to 3 degrees by the end of the century. Let me talk about the sensitivity analysis. So many of these parameters are extremely uncertain. And so we perform kind of the uncertainty exploration of the model is an important part of this. And so we do two types, and I'll show you both. One is a one-at-a-time sensitivity analysis, where we're just kind of taking these parameters and moving them up and down in hopefully a more or less consistent way. And then we also do a full Monte Carlo sampling, where that will account for kind of uncertainties, interactions between these parameters in this uncertainty space. So this is showing you that one-at-a-time sensitivity analysis of just moving these parameters up and down. What you see, and I've also included here some of the parameters of the discount rate as well. And so, as is kind of well known, like there's this high sensitivity to these parameters, to these discounting parameters, right? Like the pure rate of time preference. But what you also see is at least a fairly similar magnitude to some of these parameters that describe how climate change affects natural capital, right? So the damages parameter, as well as how natural capital enters into the production function and the utility function. This is showing you the result of this Monte Carlo sampling. And to show this, what we do is we fit a random forest model to the output. And so here I'm showing you two types of output, right? The carbon tax in 2020 and the temperature in 2100. That's on the right. And the way to understand this graph is that the kind of higher up in the column the variable is, that is the higher, the more important in explaining the variation in the output across across this sampling scheme. And so once again, you see these damages to natural capital show up here. That getting these damages kind of right, like really, is going to drive a lot of variance in the optimal climate policy. But also these questions about how substitutable are natural goods in either the production function or the utility function, as well as how important is this in the production function. So that's the kind of adjusted total factor productivity. And then just in the last few minutes, I want to spend a minute to talk about the question of, well, can we do anything about these climate change impacts on natural systems other than reducing greenhouse gas emissions? And if we can, how does that change what we think of as potentially the optimal policy? And so here we're thinking about this idea of defensive investments, or you could think of them too as kind of adaptive investments. And the question then is, can we invest so as to reduce the impact of climate change on natural capital? Green DICE, this model I just showed you, kind of assumes that the only way to reduce impacts to natural capital is through greenhouse gas mitigation. But, we know that as a society, we spend time and money and effort on kind of restoring, improving kind of natural systems, right? And here I'm just showing you the picture of flying the cranes. This is like trying to restore these crane species, and they need to be taken on their first migration. And so people kind of fly them down using a microlight, right? So we think that there is things people can do to kind of mitigate potentially some of these impacts. And so what we do here is we introduce a third optimization variable into the model. So in addition to the mitigation rate and the kind of capital savings rate, we introduce a kind of natural capital control variable. And we do this in two ways, and you'll see why I'm presenting them separately. So the first option is what we call, it allows you to convert some of production, rather than putting it to consumption or putting it to capital stock, reduce the from global warming. And we use a convex cost function, so this is showing you the effect of these adaptive investments. What you're seeing is that these are acting as partial substitutes, so that as the cost of these adaptations come down, which is the blue line here, you're getting results that look much more like the kind of standardized mitigation trajectory. And then we also allow, instead, what we call the adaptive investment pathway, we call the asset investment pathway. And what that does is allows you to just take money and kind of take some of your production and just invest it directly into the natural capital stock, in the same way that you kind of have a savings rate that allows you to invest in the manufactured capital stock. And we define a price of this asset. We define it relative to the manufactured capital asset, based on the kind of discounted welfare of those two asset investments. And the reason why I'm showing this separately is because the results look really quite different. And what you see here, what you're seeing is that if we relax the constraint on the stock of natural capital and we allow for this diversion of economic production into that capital stock, what you see is a slightly crazy result where you kind of you invest a huge amount of global production immediately into that capital stock, and so this is actually has very little to do with climate change. What this is showing you is that the welfare benefits in this model of just having more natural capital are very high. So what that suggests is that either the current stock of natural capital is kind of suboptimally low, and or the welfare effects are overestimated in green dice. And probably it's, we know that there are market failures around, the protection of natural systems. So probably it's both of those happening at the same time. So the conclusions, sorry, I can't see my slides. Natural systems are kind of directly exposed and vulnerable to climate change. If natural capital plays a particular role in supporting economic production and welfare, then it has particularly important implications for the welfare maximizing emissions trajectory. The central estimates kind of increase the social cost of carbon by a lot, and really change that optimal emissions trajectory. There's high sensitivity to like very uncertain parameters, but in the damage function, but particularly in the production function. And then the availability of adaptive investments is important and can function as partial substitutes for mitigation. So thanks so much for the opportunity to present, and I'm looking forward to the discussion.
Thank you.